Imagine the night sky erupting in a blaze of glory. A new star, brighter than any other, suddenly appears, captivating observers across the cosmos. This isn't science fiction, it's the spectacular death throes of a star, a supernova. These celestial explosions are some of the most violent and beautiful events in the universe. They mark the end of a star's life, but also the beginning of something new. Supernovae are crucial for the cosmos. They seed the universe with the building blocks of planets and life itself. Join me as we delve into the heart of these cosmic fireworks, unraveling their secrets and marveling at their explosive beauty. Prepare yourself for a journey through the cosmos. So, what exactly is a supernova? Put simply, it's a star's explosive demise. It's the biggest and brightest explosion we know of. Imagine the energy of a billion suns unleashed in an instant. That's the power of a supernova. But they are not just explosions. They are transformative events that shape the very fabric of the universe. Not all stars meet this dramatic end. Our sun, for example, will not go supernova. Instead, it will end its life as a white dwarf, a stellar ember slowly fading into oblivion. Stars, those twinkling beacons in the night sky, are not eternal. They are born, live, and die, just like everything else in the universe. Their lives are governed by a delicate balance between gravity and the outward pressure from nuclear fusion in their cores. For much of their lives, stars exist in this state of equilibrium. But what happens when a star exhausts its nuclear fuel? The answer, my friends, is where things get really interesting. Not all supernovae are created equal. One way to classify them is based on what triggers the explosion. Type 1 supernovae occur in binary star systems, where two stars are locked in a gravitational dance around each other. One of these stars is a white dwarf, the dense remnant of a sun-like star that has exhausted its nuclear fuel. The other star can be anything from a giant star to another white dwarf. White dwarfs are incredibly dense. Their gravity is so strong that even a teaspoonful of their material would weigh as much as a mountain on Earth. This intense gravity allows them to pull material from their companion star. As the white dwarf accretes more and more material, it eventually reaches a critical mass, known as the Chandrasekhar limit. Once this limit is crossed, the white dwarf can no longer support itself against its own gravity, and it explodes in a spectacular supernova. Section 5 Type 2 Supernovae, the dramatic end of massive stars. While Type 1 supernovae are fascinating, Type 2 supernovae involve a different kind of stellar drama. These explosions mark the dramatic demise of massive stars, those at least 8 times the mass of our Sun. These stellar giants live fast and die young. As a massive star fuses heavier and heavier elements in its core, it eventually reaches a point where it can no longer produce enough energy to counteract gravity. The core collapses in on itself in a fraction of a second, triggering a shockwave that rips through the star, blowing it apart in a colossal explosion. This is a Type 2 supernova, a truly awe-inspiring event. The intense heat and pressure during a Type 2 supernova forge heavier elements such as gold, silver, and uranium, which are then scattered across the cosmos. Section 6. Supernovae as cosmic lighthouses, illuminating the universe. Supernovae are not just beautiful explosions, they are also invaluable tools for astronomers. Remember those Type Ia supernovae with their standard brightness? They act like cosmic lighthouses, allowing astronomers to measure distances across the vast expanse of the universe. By comparing the apparent brightness of a Type Ia supernova to its known intrinsic brightness, astronomers can calculate its distance. This technique, known as using standard candles, has revolutionized our understanding of the universe's expansion. In the late 1990s, observations of distant Type Ia supernovae led to the astonishing discovery that the universe's expansion is accelerating, driven by a mysterious force we now call dark energy. This discovery earned the scientists involved the Nobel Prize in Physics in 2011. Section 7 Heavy Metal Factories, Supernovae, and the Elements of Life. Where do the elements that make up our planet, our bodies, and everything around us come from? It's a question that has intrigued humans for centuries. The answer, it turns out, is intimately linked to supernovae. The Big Bang produced mostly hydrogen and helium, the lightest elements. Heavier elements, such as carbon, oxygen, and iron, were forged later in the fiery hearts of stars. Massive stars, in their final act of creation, play a crucial role in this cosmic alchemy. The intense temperatures and pressures during a Type II supernova create an environment where nuclear reactions can occur at an astonishing rate. These reactions fuse lighter elements into heavier ones, producing all the elements on the periodic table up to and including iron. During a supernova, a process called neutron capture occurs, where atomic nuclei capture neutrons, creating heavier and heavier elements. This material enriches the surrounding interstellar medium, providing the building blocks for future generations of stars and planets. Section 8. Supernova Remnants. Echoes of stellar cataclysm. The explosive death of a star leaves behind more than just scattered elements. It also creates a breathtaking spectacle, a supernova remnant. This expanding cloud of gas and dust, the shattered remains of the star, glows brightly for thousands of years after the initial explosion, radiating across the electromagnetic spectrum. These remnants are not just visually stunning, they also provide crucial information about the supernova explosion and the star that created them. By studying the expansion rate and composition of the remnant, astronomers can learn about the energy of the explosion, the type of star that exploded, and the environment in which it lived. One of the most famous supernova remnants is the Crab Nebula, the result of a supernova observed by Chinese astronomers in 1054 AD. Section 9. Famous supernovae throughout history, from ancient tales to modern marvels. Supernovae have captivated humans for centuries. Long before the invention of the telescope, ancient civilizations recorded these celestial wonders, often attributing them to divine intervention. One of the earliest recorded supernovae is SN 185, observed by Chinese astronomers in the year 185 AD. This guest star, as they called it, remained visible in the night sky for 8 months before fading from view. Another famous supernova, SN 1006, was observed by astronomers around the world in the year 1006 AD. This supernova, which occurred in the constellation Lupus, was reportedly brighter than the planet Venus, and was even visible during the daytime for several weeks. In more recent times, the advent of powerful telescopes has allowed astronomers to observe supernovae in unprecedented detail. Today, astronomers continue to scan the skies for supernovae, using sophisticated telescopes and automated surveys to detect these fleeting but spectacular events. Section 10. Searching for supernovae, unveiling the secrets of exploding stars. The hunt for supernovae is a global endeavor, with astronomers around the world collaborating to detect and study these cosmic explosions. Large-scale surveys such as the All-Sky Automated Survey for Supernovae, ASAS-SN, and the Zwicky Transient Facility, ZTF, scan the sky every night looking for changes in brightness that could indicate a supernova. These surveys generate massive amounts of data, which are then analyzed by both humans and sophisticated algorithms. When a potential supernova is detected, astronomers use larger telescopes to confirm the discovery and study its properties in detail. These observations provide valuable information about the supernova's distance, luminosity, and the composition of the ejected material. Each new discovery provides a piece of the puzzle, helping us unravel the secrets of these cosmic cataclysms and their profound impact on the universe. Section 11. Conclusion. The enduring allure of supernovae. From the ancient astronomers who marveled at their sudden appearance in the night sky to the modern scientists who study them with cutting-edge telescopes, supernovae have captivated the human imagination for centuries. These celestial explosions, marking the dramatic deaths of stars, are not just visually stunning, but also crucially important for the evolution of the universe. Supernovae seed the cosmos with the heavy elements that make up our planet, our bodies, and everything around us. They act as cosmic lighthouses, illuminating the vast distances of space and revealing the secrets of the universe's expansion. As we continue to explore the cosmos, supernovae will undoubtedly continue to surprise and amaze us, offering new insights into the workings of the universe and our place within it.